Welcome to press course number 96, and today we're talking about the effects of sweep angle on airfoil aerodynamics. So in particular, we're talking about forward sweep. And this is a little bit less common than backward sweep, but it is quite common in certain areas. So to look at this, we're going to look at a paper called Study on the Influence of Swept Angle on the Aerodynamic Characteristics of the Cross-Section Airfoil of a Variable Swept Wing Aircraft. This is open access, so you can find it in the link in the description. So the sweep angle is used often for a bunch of different reasons. You can use it for changing the critical Mach number in terms of going faster or slower. You can use it in terms of changing the stability of an aircraft and the lift production and drag production. So we're going to be looking at the lift production, drag production, and the pitching moment. And these are three very important parameters for any aircraft and any airfoil. So they say the variable swept wing layout aircraft is a typical variant of aircraft, depending on which field you're in, of course. And this can change the wing grazing angle according to its needs, but the grazing angle will bring serious changes in aerodynamic characteristics, which have an impact on flight performance and safety. So in other words, you can change whether the wing is pulled forward a bit more or backwards a little bit more. And this does change the stability parameters such as longitudinal, lateral, and yawing stability of an aircraft. So it is necessary for the aircraft to achieve the evolution of the configuration with changes in flight conditions. So in other words, depending on the flight conditions, you want to have different configurations to optimize your performance. With the change of the grazing angle of the wing, so the sweep angle, the relative thickness of the cross-section of the airfoil will change with the parameters of the airfoil, which will have a great influence on the aerodynamic performance of the overall wing. So what happens is, this is a little bit of a difficult concept to just describe with words. It's often very good with a picture, but I'll do my best in this podcast, and we'll see some pictures later on. If you want to see the video, you can see it on our YouTube channel. Otherwise, I'll describe it here. So imagine you have a regular straight wing, and you have a regular airfoil profile. Let's say a NACA 0020, so a very simple, common, thick airfoil shape. Very simple. But then let's say let's say that the wing chord is 1 meter. If you then pull the wing back at a 45-degree angle, that wing chord will now be, I think, 1.414 meters from basic trigonometric principles. So the chord is longer because the chord is measured from the leading edge to the trailing edge in a straight line of the free stream direction. But the thickness of the chord hasn't changed. The thickness of the airfoil has not changed. So the thickness to chord ratio is now going to be smaller in this particular case. Because the chord is longer, the thickness is the same, the thickness to chord ratio drops. So let's say if you had a thickness of, is it NACA 0020, so the thickness should be 0.2 meters if the chord is 1 meter. So that's 20%. If you have a straight wing, if you pull it back to 45 degrees, the chord is now 1.4 meters. So the thickness to chord ratio is 0.2 divided by 1.4, which is, what's that, 0.07. Wait a second, no, let me calculate that quickly. It's just, sorry, that's 0.14, not 0.0, so 0.14. So it's gotten smaller from 0.2 to 0.14. Now, depending on how you sweep the wing, if you sweep it forward, if you sweep it backwards, where you sweep it along, which pivot point, it changes the thickness, and we'll get into some differences later on. So that's how the sweep angle can change the thickness of the airfoil and effectively the cross-sectional area, the thickness to chord ratio. And that means that the aerodynamic performance of the wing changes. So it's necessary to look into how this affects aircraft performance. So in this paper, they say in order to make the wing of the variable swept wing aircraft change smoothly in a state of a flat wing, forward swept wing, or delta wing, this paper selects a NACA 0006 thin symmetrical airfoil as the basic airfoil of the variable forward swept aircraft. So a note on the NACA 0006, this is a very thin wing. It's only a 6% thickness chord ratio. It has no camber. So it's getting close to the point where you wouldn't really want to use an airfoil this thin or thinner because it is a little bit too thin. And the problem with thin airfoils is they often have a fairly dramatic stall profile, and also they usually don't produce as much lift as thicker airfoils. However, at high speeds, they do become better in terms of their lower drag. So there's a trade-off here. In this particular case, we're not looking at very high Mach numbers, so an NACA 0006 is quite thin, but they have a picture here showing the the wing itself. So they say the wing is composed of an outer wing and an inner wing hidden in the rear of the fuselage in a flat wing state. The geometry and contour are shown in figure 1. So what does this mean? So if you think about let's say you have a regular aircraft, a regular airplane, and you have its wing. Now, to sweep this wing forward or backwards, if let's say you pivot it around the leading edge, if you pivot it forwards, now there's going to be a gap between the trailing edge root and the fuselage because now you've pulled that part a lot forward. You need extra material to make up that little bit here, that gap here. Likewise, let's say you pivot the wing around the trailing edge where it meets the fuselage. Let's say you pull back now. So there's going to be a gap between the leading edge root and the fuselage. Alternatively, if you were to pivot it around the trailing edge where it meets the fuselage, so you now push the wing forward, there's going to be the wing's going to start driving into the fuselage, that wing root at the leading edge there. So you need to have a slit inside the fuselage where extra wing can be accommodated. So when you pull it out, it can either take up that slack that you've created, or it can go into the fuselage as you pull it in that direction. So that's what they're talking about here. Now in figure 2, in order to fully consider the convenience and responsiveness of airfoil interceptions, the airfoil section of Group A, so we'll talk about these two different groups first. Group A represents the rotation of this wing around the leading edge at the wing root. The Group B airfoil series represents the rotation of the wing around the trailing edge at the wing root. So I mentioned earlier how you can rotate it about different points. So what happens is if you rotate it around the leading edge, this changes the relative thickness to chord ratio of the wing differently to if you were to pivot it around the trailing edge. And if you look at the figure here in figure 1, it's a little bit easier to understand why that is. And the reason why is because the trailing edge is at an angle. It's tapered the wing, but it's not tapered from the leading edge, it's tapered from the trailing edge. So that means that as you rotate the wing backwards, that trailing edge is going to become more and more horizontal. So as that happens, the wing changes the thickness chord ratio. And then once you move past a certain point, it will then start to become more angled again, just due to basic trigonometry. So what happens is with Group A airfoils, which are pivoted about the leading edge pivot point near the wing root, as you increase the sweep forward angle, effectively the thickness chord ratio, but the chord reduces dramatically in length. Alternatively, if you pivot it around the trailing edge point, the wing root at the trailing edge, the chord becomes really long, so almost double once you get to a sweep angle of 60 degrees forward. So what this does is it changes the thickness and thickness chord ratios, which we'll go through now. So the relative thickness of the airfoil of Group A and Group B, as a function of the forward sweep are shown in Table 1. What this shows is that the relative thickness of the airfoil Group A first increases and then decreases after a certain sweep angle. And that's what I was mentioning earlier, where because the trailing edge is angled as well, once you get to a certain point, it goes from being angled to horizontal back to angled, and this changes the thickness chord ratio. So it starts off with a 0 degree sweep angle with a 6% thickness chord ratio because it's NACA 0006. As you go up to 40 degrees, this thickness chord ratio increases to 9.26. But once you go past that point to 60 degrees, the thickness chord ratio drops back to 8.29, which is still greater than the 6% at 0 degree sweep angle, but it's still not as great as the maximum of 9.26. Now, looking at Group B, which is the airfoil when you pivot it around the trailing edge at the wing root, as you increase the sweep angle, the thickness chord ratio just keeps dropping. So it starts off at 60 degrees, and then by 60 degree sweep angle, it's down to 0.88%, which is really thin. It's almost like a flat plate. And generally speaking, flat plates are not good for flying because they are only good for a very narrow range of angles of attack. So to look at these sweep angles, they did some CFD, they did RANs, and the terminus model that they used was the SA, so Spalart-Almaros. And this is an important point to note because the Spalart-Almaros terminus model, there are a bunch of terminus models for RANs and URAN simulations. Spalart-Almaros is one of them. And this is one of the earliest terminus models going around. And it's a very interesting one because it's ideally suited to this type of application, wings. But if you use it for wings, then it is quite accurate. If you use it though for other situations, for example, a bluff body or one that has quite a lot of turbulent flow, or even a little bit of turbulent flow, it starts to break down very quickly and not become very accurate. So the SA turbulence model is only good, and it's very good for this particular application. Other applications, you should probably stay away from it and use other ones, such as my favorite SSD, K Amiga. That's because that's just a very robust one that works in almost every situation. You don't need to do too much thinking about whether it's good or not. You can just use it. But the SA model is good for this particular application. Another point to note is that they have an ideal temperature of 288.15 Kelvin. Now, to note this, if you were to use experiments to validate this CFD, you would need to measure the temperature, barometric pressure, and humidity in your wind tunnel to make sure you get the right density. And of air, because air does change in density by about 2 to 4% every day, and that will make your CFD validation data incorrect. So you need to measure the air density. And to do that, we make an instrument called the Atmosphere Hawk. You can find it in the link in the description. It does it for you very accurately, so you get rid of that error in your wind tunnel experiments. And so your regular data for your experiments are good, and your validation data for your CFD that you use are also good. So pick one up in the link in the description. So let's get back to these results now from their CFD in figure 3. They have the variation of the lift coefficient of each airfoil group with the angle of attack under a Mach number of 0.2. Now, while I mention Mach number, we'll cover this a little bit later, how this affects the performance. But let's just continue now thinking about the lift coefficient. They say for the A set airfoils, which are the group of airfoils that pivot around the leading edge, and remember, it starts once you start increasing the sweep angle forward, the thickness starts to increase up to a certain point, and then it drops off. The thickness chord ratio, sorry, I should say, not thickness, because the thickness does stay constant. It's just that the chord changes. So the thickness to chord ratio increases up to 40 degrees, and then once you go past 40 degrees, the thickness chord ratio drops. So they say, in this state, when the angle of attack is less than 8 degrees, the lift coefficient increases linearly with angle of attack, which makes sense, up to the maximum lift coefficient. That's what we want. That's normal. As this forward sweep angle increases, the maximum lift coefficient first increases, then it decreases. And the maximum lift coefficient is reached when the sweep angle is 20 degrees forward. Moreover, the increase of the forward sweep angle also causes the stall angle to increase first and then decrease. So in other words, the stall angle is proportional to the thickness to chord ratio of the wing. And this makes sense because we can look at some limiting cases. For example, a flat plate, the stall angle is very low. It's like 2 degrees or so. And it sucks for producing lift past that. But if you go to a very thick airfoil, for example, a NACA 0020 or NACA 0030 perhaps, the stall angle dramatically increases. So this is what we're seeing here, so that makes sense. So they also say that the stall angle attack is largest when you have a sweep angle of 30 degrees. So the maximum lift coefficient is largest when you have a sweep angle of 20 degrees, but the maximum stall angle, the stall angle is greatest when you have a sweep angle of 30 degrees. So there's a trade-off there, whether you want to get more angle of attack range or whether you want to get a higher lift coefficient. You can choose 2 different sweep angles. When the angle of attack is increased, they say the negative pressure zone of the leading edge of the airfoil increases, the suction increases, and at the same time, the airflow separation begins to occur at the trailing edge of the upper surface of the airfoil. So this is important, how this separation is occurring. Now, I should mention here some different separation patterns. So for typical airfoils like the NACA series here, the typical way that they separate is from the trailing edge, and then as you increase the angle of attack, this separation slowly migrates towards the leading edge until the entire airfoil has separated. Now, other airfoils, for example, a very thin airfoil, typically will just separate all at once, and sometimes even separate from the leading edge and then go backwards to the trailing edge. It really depends on the airfoil. In this particular case, though, they're following a very standard way of stall, which is from the trailing edge, and you slowly migrate upstream until the entire airfoil has separated with increasing angle of attack. So for the B set airfoils, which are airfoils that are pivoting around the trailing edge route, when the sweep angle is less than 20 degrees, the stall angle of attack and the maximum lift coefficient decrease with increasing forward sweep angle. while the maximum lift coefficient increases with an increasing sweep angle. When the thickness of the section airfoil is small, the lift coefficient will increase with the increase of the forward sweep angle. For example, the airfoil thickness of the B group is less than 6%. So this makes sense. Another thing to note is there are really like two halves to this airfoil set. Like when you have a sweep angle of 20 degrees or less, the stall angle attack is significantly higher than when you have a sweep angle greater than 20 degrees. So when you have 30 degrees, 40 degrees, 50 degrees, 60 degree sweep angles, the stall angle attack is pretty much always like is about 7%, 7 degrees, sorry. But if you have a lower stall angle, a more shallow stall angle, then you can get stall angles up to 10 degrees and they're a bit more stable. So that's interesting, that dichotomy there. Let's move on to figure 4 now, which looks at the influence of the Mach number on lift characteristics when the sweep angle changes. So in figure 4, they have all airfoils at only 4-degree angle attacks, and they're changing the Mach number to see how this affects the lift coefficients. So I just want to cover here briefly what I was mentioning earlier about Mach numbers. So the Mach number is a very important parameter because it changes the density of air to begin with, but it also can potentially allow the onset of what's called the critical Mach number. So it's not sonic flow. The critical Mach number is the number at which you need to be traveling at for your object to experience sonic flow at some point over it. So for an airfoil, because when the flow comes first, it hits the leading edge, then it travels over each side and it accelerates, particularly over the top, the suction side. When it accelerates, the speed obviously increases, so you're getting closer to the sound barrier than the leading edge is. So that means that you can actually have sonic flow on your airfoil, even though the free stream velocity is not a Mach number of 1. It can be lower than that. So that's what's called the critical Mach number. And what this means is that a thicker airfoil would have a lower critical Mach number, which means that, let's say you have a free stream velocity of 0.9 Mach number, you can have a critical Mach number of that, which means you're getting sonic flow at that point, compared to a very thin airfoil, which may still be completely subsonic. So the greater the thickness of the airfoil, the lower the critical Mach number is. So this is why this is important for this particular application. Because as you change the sweep angle, the chord changes length, thickness to chord ratio changes, and that changes the critical Mach number. So I just wanted to talk about that here. They don't go too much into that here. They have much lower Mach numbers here, but I wanted to talk about that because it does feed into this idea. So they say that in figure 4, it can be seen from the figure that the lift coefficient of each airfoil group increases with increasing Mach number. And the rate of increase of the lift coefficient increases with the increase of the Mach number. At the same Mach number, as the forward sweep angle increases, the lift coefficient gradually decreases. So in other words, for the A set airfoils, as you increase the Mach number and you have the angle attack still 4 degrees, the lift coefficient drops with increasing sweep angle. Now with the B set airfoils, which mean that they are getting thinner with increasing sweep angle, as you increase the Mach number, they start to converge a little bit, so they will start to produce a similar amount of lift. Why that is, I'm not too sure. It may be something they say here that when the Mach number is increases 0.6, the leading edge of the airfoil gradually generates a shock wave. Now, that's quite interesting because that seems to be quite a low Mach number for that to start happening, but I didn't see their CFD that may be occurring. The appearance of the shock wave makes the absolute value of the leading edge pressure of the airfoil larger, and the airfoil of the negative pressure zone is further increased, so the airfoil lift coefficient has increased dramatically with increasing Mach number. Now, with this convergence, that may be due to the limiting case of the sound barrier. I'm not too sure there. So let's move on to figure 5, which now we're looking at the influence of angle attack on resistance of drag when the sweep angle changes. So figure 5, it shows under a Mach number of 0.2, the variation of the airfoil drag coefficient with the angle attack at different forward sweep angles. For the A airfoils, which are pivoting about the leading edge route, which means that as you increase the sweep angle, it gets a greater thickness to chord ratio and then drops a little bit after that. With these airfoils, with increasing sweep angle, the drag coefficient generally increases because the pressure drag increases. So let's just talk about this briefly here. So for this type of airfoil, which is really just a 2-dimensional airfoil, there are only 2 types of drag in this Mach number. So there's skin friction drag and pressure drag. Skin friction drag comes from just the flow going over the surface and creating friction that way through viscosity. Pressure drag occurs due to a deficit in pressure downstream of the airfoil compared to upstream. So if you integrate the pressure upstream into force and you compare that to the pressure downstream integrated into force, you see that there is a force difference, which results in a drag. And as you increase the angle of attack, the pressure drag typically increases. And now we have here that when the sweep angle increases, generally speaking, the pressure drag increases as well. And that's because the thickness chord ratio increases. And this is a great way to increase the pressure drag, which you don't want. For the B airfoils, which when you increase the sweep angle, the thickness chord ratio drops, because it gets to a point where the more highly swept airfoils still at a much lower angle of attack, the drag of these highly swept airfoils is much greater, even at only 4 degrees. So in other words, because these airfoils are getting thinner and thinner, the stall angle attack drops dramatically. And so that means that you're getting a lot more pressure drag at these lines of attack, which means that as you increase the sweep angle, you're getting a lot more pressure drag and drag overall simply because of this phenomenon. So that's not very good. You want to keep the sweep angle low in this particular case. So finally, we're going to talk about the pitching moment. And this is very important because the pitching moment affects dramatically the stability of the aircraft. So the pitching moment is the tendency for an object to either pitch forward or backwards. And for an aircraft, you want to have a negative pitching moment because you want the airfoil to be inherently stable, which means that, let's say you're flying around and you're at an angle of attack of 5 degrees. If you have a positive pitching moment, it means that the airplane wants to naturally pitch up more, so nose up. If that happens, you start increasing the angle of attack, which means you increase lift even more, and that will generally increase the pitching moment even more. And then you get this cycle happening to the point where you get to an angle of attack, which is so high that you start stalling. You lose lift, and that's bad. You then fall out of the sky. Alternatively, if you have the point where the aircraft where it has a negative pitching moment, then if you're at an angle of attack of, let's say, 5 degrees, you're flying around, the aircraft naturally wants to pitch down, so nose down. That means that the lift that you will produce naturally will drop, and that's stable because now you're going to an angle of attack of 0 degrees, and you can fly around. You may not be able to fly, but you can glide, and that's far more stable than losing lift altogether when for pitching too high. So that's why we want a negative pitching moment coefficient. So for these airfoils, they say in figure 7, they have the pitching moment plotted against the angle of attack. And they say generally as the relative thickness of the airfoil increases, the pitching moment coefficient drops. So for the A series airfoils, increasing the sweep angle reduces the pitching moment coefficient. For the B series airfoils, increases pitching moment, increases the pitching moment coefficient. So for one set of airfoils, the A set, the increasing sweep angle is beneficial for the pitching moment. For the B set, it's detrimental. And that's due to the change in the thickness chord ratio, generally. So, in conclusion, they have 4 different points that they want to talk about. Point 1, when the grazing angle of the wing changes, the relative thickness of the section airfoil and other parameters will also change, and the aerodynamic characteristics will change accordingly. When the angle of attack changes, this is the second point, the lift coefficient decreases and the increase of the forward sweep angle for the cross-sectional airfoil with large relative thickness. So in other words, as the angle attack changes, the lift coefficient decreases with increasing forward sweep angle, and the cross-sectional area airfoils with larger relative thickness, this happens for. Point 3, when the angle attack changes and the drag coefficient of each airfoil increases with increasing forward sweep angle. And point 4, when the angle attack changes, the pitching moment coefficient decreases with increasing forward sweep angle for cross-sectional airfoils with larger relative thicknesses. So this is a very robust way of looking at it. Instead of thinking about the sweep angle, you look at the effect that the sweep angle has. So you can now relate this back to any sweep angle, as long as you know what the effect of the relative thickness is, which is just a geometric parameter. So that's in this podcast. Make sure to like, subscribe. And if you want to get better at CFD yourself, so we're talking about the Spallet-Almaras turbulence model, for example, earlier, and a bunch of other things. If you want to get better at CFD, check out our courses, which we go through this and much more. If you want to get better at theory, we also have courses for that as well, links in the description. And if you want to make your CFD more accurate in terms of your validation data and your experimental data more accurate, check out the atmosphere hawk because that accurately measures the density of air for you. And remember that changes every day. Let's say you turn up at 9 a.m. and your wind tunnel density air might be 2% or 4% different than when it is what it is at 4 p.m. later in the day. So you want to get rid of that error. So we make the atmosphere hawk for that. Check out that in the link in the description, and I'll see you in the next podcast. Peace out, amigos.